Every means of producing energy also requires the consumption of energy and physical resources. For example, fossil fuels need to be extracted, transported, refined and burnt in suitable engines or power plants. Wind and wave power similarly require turbines to be produced and maintained, while PV solar technologies require the manufacture of appropriate panels. None of this hardware just springs from thin air, and none of it lasts forever. Any sensible assessment of any energy source therefore has to be mindful of its net energy contribution. Net energy is a measure of the energy obtained from an energy source after accounting for the energy consumed in its production. Those who analyse net energy work with a ratio of energy output to energy input known as EROI, or the energy return on investment. So, for example, if the production of 20 units of energy requires the consumption of 1 unit of energy, the EROI of the involved energy source is 20 to 1. Back in the 1930s, the easiest to extract forms of petroleum gushed freely from a well and had an EROI ratio of up to 100 to 1. Today, however, such very easy to extract crude oil is rare, with petroleum having a global EROI of no more than 40 to 1. The global EROI value for petroleum will also diminish further as crude oil gets harder and harder to locate and extract. Those in denial about peak oil often pin their hopes on non-conventional oil or biofuels. Unfortunately, all such petroleum alternatives have low net energy yields. For example, the EROI for shale oil is typically about 5 to 1, while oil extracted from oil sands has an EROI of no more than 7 to 1. The net energy yield of biofuels is even lower at no more than 3 to 1. While cited EROI ratios for traditional coal power stations are up to 80 to 1, clean coal technologies only achieve around 5 to 1. Hydroelectric power has an EROI of maybe 30 to 1, while both natural gas and nuclear fission deliver about 10 to 1. Wind power can deliver a potential EROI of up to 18 to 1, although usually far less. PV solar delivers a maximum EROI of about 7 to 1, while reliable EROI values for concentrated solar power and wave power are not yet established, if not expected to be very high. Net energy values are extremely difficult to calculate and hotly contended. Nevertheless, no serious analyst disputes that the global net energy of petroleum continues to fall. Nor is there any disagreement that the net energy obtained from all major alternative energy sources is far lower than that of conventional fossil fuels. What all of this means is that, while alternative energy sources will be able to fuel the world of tomorrow, they will not be able to power a clone of today. Indeed, by 2030, to go on consuming energy at our current level would require not just a substantial switch to alternative energy sources, but an increase in the scale of a global energy sector of several 100%. And this is simply not a realistic proposition. In addition to food, all cities currently require significant natural resources to meet their raw energy needs. However, alternative technologies, including solar cells, rooftop wind turbines, ground source heat pumps, and methane power plants fueled from domestic rubbish, could see future cities becoming at least partly energy sufficient. Micro power generation may even extend to piezoelectric paving slabs to generate electricity from our footsteps, as well as hydraulic plates in road surfaces that would generate power as vehicles drive over them.
Most of the region's energy and environmental systems are now located close to the populations they serve. This is made possible through the miniaturization and integration of these technologies and their co-location in residential neighborhoods at the Resource Management Center, or RMC. From the exterior, the RMC appears to be little more than an attractive two-story civic building. But on the interior, an impressive array of technology generates, stores, and controls the flow of the neighborhood's energy and receives, reclaims, and recycles its water and solid materials. As we approach the RMC, we notice the expansive array of solar, photovoltaic, and thermal panels that shade the building's elevation. They are producing both energy and hot water for the surrounding community, while they cool the building's interior. We also notice a rooftop plaza capped by a curious antenna. What appears to be moving just above the plaza are rotor blades of a highly efficient wind turbine, converting the coastal airflow into energy. What appeared to be a two-story structure from the exterior is now clearly an expansive four-story structure, with two below-grade floors now visible. Before descending further, we see the neighborhood's PMV fleet operations and maintenance center. Here the PMVs are refueled with hydrogen, produced by the wastewater treatment facility below. The PMVs also share their electrical energy with the RMC's battery banks and serve as mobile sources of electricity for remote activities outside of the neighborhood's electrical microgrid. Private companies maintain showrooms on the PMV level, enabling neighborhood residents to choose from among a variety of models and amenities available to customize their annual PMV leasing programs. And sophisticated computer systems are housed here that manage both the PMV system and the two-way flow of energy between the RMC and its residential and commercial users, and the region beyond. At the ground floor level, we see an extensive bank of hydrogen fuel cells. Along with renewable technologies, these fuel cells are the combined cooling, heating, and electricity generation source for the neighborhood. These cells are electrochemical devices that directly convert hydrogen or hydrogen-rich fuels into electricity without combustion. Although they resemble batteries, fuel cells never need recharging or replacing and can consistently produce electricity as long as they are supplied with hydrogen and oxygen. This process is much more efficient than traditional thermal power plants, converting up to 80% of the chemical energy in the fuel into electricity. Heat from the fuel cells is collected and sent a story below to aid in the drying and vitrification of sanitary solids. The heat is also used to chill water for district cooling uses in the neighborhood. Sanitary water flows from the community are received at the RMC through separate gray and dark water intake pipes. Utilizing an electrical current from the RMC's solar photovoltaic system, the gray water flows are electrolyzed to produce hydrogen and oxygen for the fuel cells. Dark water flows are sent to an anaerobic decomposition chamber where bacterial processes produce both hydrogen and methane. Some of this methane is reformed to produce additional hydrogen, while the balance is burned in a glass furnace that turns the remaining sanitary solids into a molten hot material. This material is then quenched in cold water to produce a fine glass aggregate for use in the production of building materials. Recycling of sanitary solids in this manner proves to be far more sustainable than the use of these solids as an agricultural fertilizer, which only recycles trace metals and salts back into the food chain. All remaining waters from this system are then blended and purified with the other major water supply in this particular metropolitan region. At the lowest level, salt water reaches the RMC through a network of inland distribution centers fed by coastal pumping stations and powered by inline micro-hydro turbines. The salt water is sent through an energy-efficient capacitive deionization filtration system utilizing membrane-based seawater treatment technologies. The output is potable drinking water, as well as solid blocks of salt. The water is fed back to homes and businesses through a network of underground pipes, while the salt is sent to regional collection centers for use in a wide variety of industrial processes and commercial products. Essentially, all waters in the region are now recycled for multiple uses. Although the RMC produces most of the energy to meet the needs of its neighborhood, it also receives supplemental energy from remote sources, distant wind farms, geothermal fusion, and in the case of this region, ocean thermal and wave power facilities also produce and send electricity to the RMCs through underground superconducting conduits. The RMCs within the region also share energy resources with each other through a microgrid, similar to the one each shares with its neighborhood service area. Finally, and most surprisingly, some energy is sent from the RMC to users through wireless transmission. These transmissions energize small appliances and portable electronics in the home and office, eliminating the needs for excessive structural wiring in many buildings. Home, as always, is where the heart is. It's also where the heart of energy efficiency is, now a priority for its occupants. Spurred on by the advances in the miniaturization of energy technologies, their integration in building materials, and sustainable design practices, many buildings now produce as much or more energy than they consume. Siting of buildings for optimal solar orientation, rooftop wind scoops, vegetation, and automated clerestory windows all take full advantage of natural light, precipitation, and airflows to illuminate and cool the interior. Solar photovoltaic wall paints and glass surfaces generate energy, while rooftop solar thermal units heat water for multiple domestic uses. Many exterior glass walls feature electronically triggered coatings that allow residents to modify opacity at will, enabling the instant placement or removal of windows of any size. Modular interior walls are mobile, allowing for the rapid reconfiguration of space to suit any function. Furniture, internal decorative materials, and floor surfaces are comprised of recyclable materials, such as wood, plant fibers, and resins. Most durable goods are now leased, and manufacturers' take-back and recycling programs have resulted in the practical elimination of all solid waste. Bipiping and separation of water flows from kitchen and bathroom appliances also ensures the continuous reclamation of this precious natural resource. In our sustainable urban system design for the future, human, animal, and plant communities thrive. Our primary goals: optimal usage of our energy resources,